for being here today. I'm excited to share with you one of the most elegant problem-solving techniques, dynamic programming. Now, I know that dynamic programming can sound intimidating at first, but I promise you that by the end of this video, you'll understand not only what it is, but why it's such a game changer in the world of algorithms and computational efficiency. Over the next few minutes, we are going to take a comprehensive journey through this fascinating technique, starting with the basics and building up to real-world applications that affect our daily lives. Before we dive in, let me give you a roadmap of where we are headed today. We will start by defining what dynamic programming actually is and understanding its core purpose. Then we'll explore the two essential requirements that make a problem suitable for dynamic programming. After establishing the foundation, we will work through a classic example, the Fibonacci sequence. To see dynamic programming in action, we will look at both the naive approach and the optimized approach so you can really appreciate the dramatic difference. Then, we will compare dynamic programming with pure recursion to understand exactly what makes DP special. Finally, we will explore real-world applications where dynamic programming makes the impossible possible. So, what exactly is dynamic programming? At its heart, dynamic programming is a method for solving complex problems by breaking them down into simpler, more manageable subproblems. But here's where it gets interesting. The core principle of dynamic programming is this. We think we store the solutions to subproblems so we never have to solve the same subproblem twice. Think of it as built-in a reference library. When we encounter a problem we will already solved, instead of doing all the work again, you simply look at the answer we computed earlier. This simple idea, remembering our previous work, is what transforms intractable problems into solvable ones. Now, why do you need this approach? First, it optimizes computational efficiency. Second, dynamic programming can reduce time complexity from exponential to polynomial time. Third, it's specifically designed for optimization problems where we need to find the best solution. And fourth, it finds optimal solutions, the absolute best answers to our problems. Dynamic programming isn't a magic wand that works on every problem. For dynamic programming to be applicable, a problem must satisfy two specific requirements. The first requirement is called as overlapping subproblems. This means that as we break down our problem, the same smaller problems appear multiple times. When this happens, we have an opportunity to store solutions and reuse them. The second requirement is optimal substructure. This guarantees that if we find the optimal solution to each subproblem and combine them correctly, we will get the optimal solution to the overall problem. These two properties work together to make dynamic programming both possible and powerful. Let's dive deeper into overlapping subproblems. The core concept here is that when we break down a complex problem, we find that the same smaller problems need to be solved multiple times. Imagine you are trying to find the shortest path to a network of cities. As you explore different routes, you might need to calculate the shortest path from city A to city B dozens of times as part of finding various longer routes. Without dynamic programming, we will recalculate the answer. We recalculate that the shortest path every single time. With dynamic programming, we calculate it once and store the answer. And then every subsequent time we need that information, we just look it up instantly. This difference is staggering. We are talking about the difference between solving a problem in seconds versus hours. The second requirement is optimal substructure. Here's the definition. A problem has optimal substructure if an optimal solution to the problem contains optimal solution to its subproblems. For example, if you are finding the shortest route from New York to Los Angeles to Chicago, then the portion from New York to Chicago must also be the shortest route between these two cities. This property allows us to build solutions bottom up. We start by solving the smallest subproblems optimally, then combine these optimal solutions to solve larger problems. Because of optimal substructure, when we reach our original large problem, we guaranteed to have found the optimal solution. This is fundamentally different from greedy algorithms. With optimal substructure and dynamic programming, we get the mathematical guarantee of optimality. Now let's see these concepts in action with the Fibonacci sequence. The problem is simple. Calculate the nth Fibonacci number, where each number is the sum of the two preceding ones. The sequence starts 0, 1, 1, 2, 3, 5, 8, 13, 21, 34 and so on. Mathematically, f of n is equal to f of n minus 1 plus f of n minus 2. With base cases, f of 0 is equal to 0 and f of 1 is equal to 1. This seems straightforward. But here's the challenge. What if I ask you to calculate the fifth Fibonacci number? The naive approach leads to a computational nightmare, while dynamic programming makes it trivial. The intuitive approach is a simple recursive function. If n is 0 or 1, return n. Otherwise, return f of n minus 1 plus fib of n minus 2. This is elegant and mirrors the mathematical definition perfectly. But there's a catastrophic problem. This approach has exponential time complexity, big O of n to the power n. To calculate fib of 50, this would require more than 1 quadrillion function calls. Even on a modern supercomputer, this would take years to complete. Why? Because we are recalculating the same values over and over again. To calculate fib of 50, we need fib of 49 and fib of 48. But to calculate fib of 49, we need fib of 48 again. And we recalculate it from scratch. This redundancy multiplies catastrophically. Now, let's apply dynamic programming. Instead of recursively recalculating everything, we create an array to store our results. We initialize f of 0 is equal to 0 and f of 1 is equals to 1. Or we can then use a simple loop. For each Fibonacci number from 2 up to n, we calculate it using dp of 1 is equal to dp of 1 minus 1, I minus 1 plus dp of I minus 2. Storing the result. That's it. Each value is calculated exactly once. The time complexity, big O of n, linear time. For 50 instead of quadrillions of operations, we need exactly 50 calculations. That computation that would take 10 years, it now completes in microseconds. That is the transformative power of dynamic programming. We have taken an exponentially growing problem and reduced it to a linear growth. So, let me tell you just how dramatic this difference is. For n equals 10, the recursive approach uses about 177 operations versus 10 for dynamic programming. For n equals 20, recursion needs nearly 22,000 operations while dynamic programming needs just 20. For n equals 30, recursion explodes to over 2 million operations. Dynamic programming needs only 30. And for n equals 40, we are looking at over 331 million operations for recursion versus just 40 for dynamic programming. These aren't just numbers. This is the difference between usable algorithms and completely impractical ones. This is why dynamic programming matters, why it's taught in every computer science curriculum, and why it powers so many systems we rely on every day. Let's understand how dynamic programming differs from pure recursion. In approach, pure recursion works top-down using divide and conquer. Dynamic programming works bottom-up or uses memorized top-down recursion. The critical difference is storage. Pure recursion stores nothing while dynamic programming stores results systematically. This leads to vastly different efficiency. Pure recursion often results in exponential time complexity. While dynamic programming achieves polynomial time, there is a trade-off. Dynamic programming requires additional space for storage, but we are trading a modest amount of space for an exponential improvement in time. Memory is cheap, but time is our scarcest resource. So, while pure recursion is elegant, dynamic programming is what we turn to for practical, efficient solutions. Where does dynamic programming matter in the real world? Everywhere. First, shortest path problems. Every time you use GPS navigation, TP algorithm works behind the scenes. Second, resource optimization. The KNAP problem and budget allocation use these principles. Third, bioinformatics. DNA and protein sequence alignment rely on dynamic programming. Fourth, text processing. Spell checkers use dynamic programming to calculate edit distance. Fifth, financial planning. Stock trading algorithms and portfolio optimization depend on dynamic programming. And 6. Game AI. Chess and Go programs use dynamic programming to evaluate strategies. Dynamic programming is fundamental to modern computing in ways most people never see but benefit from every day. Let me leave you with 5 key takeaways. First, dynamic programming equals recursion plus memorization. The simple addition transforms exponential problems into polynomial solution. Second, remember the two requirements, overlapping subproblems and optimal substructure. Both must be present. Third, underrate the trade-off. Dynamic programming creates space for time. And in the modern world, this is the almost always worthwhile. Fourth, dynamic programming is essential for optimization problems where you need the best solution. And fifth, this technique powers countless real-world applications affecting our daily lives. Once you learn to recognize problems with these properties, you'll see opportunities to apply dynamic programming everywhere. Thank you all for your attention. I hope this has given you a solid understanding of dynamic programming, what it is and what it matters and how it works. Thank you all.